In this video, we are going to do part 6, and that is where we implement the Crank-Nicholson method and plot the temperature profile as a function of time. And this will be done in Google Colab off of our already made script for part 3. So everything right here is what we did in part 3. And to begin implementing what we learned in our previous 2 videos by adjusting our variables to fit the new parameters of our current problem, we first double the number of spatial divisions that we have. So I'm going to copy this. And we've got nx equals 100. And then this is 2000. The thermal diffusivity, which is a float number, we have alpha equals 1 point. And then we also need to have the spatial increments. So we have delta x equals 0.5 this time. And then our time increment, which is delta t equals 0.5. And so starting a new line, we still need x to create a list of values for plotting, but we also need to adjust for the changes in variables in our x and r equations. So we write x equals numpy dot a range and in parentheses and x close parentheses and then times delta x. And so it's basically the same thing that we had up here. That's why I copied and pasted it. And so for our R equation, we are defining for our Crank-Nicholson equation. Notice that we need to divide by 2. So we end up having the exact same thing. R equals alpha times delta t divided by delta x to the power of 2. And then this is also divided by 2. So there are no parentheses. We basically just have alpha, asterisk delta t slash delta x double asterisk 2 divided by 2. So then we're going to set the initial uniform temperature to 20 degrees Celsius, and we are going to also use NX2 because the spatial divisions are different. So starting a new code, we've got t equals numpy dot full nx comma 20 dot. And I'll delete this in a second. And this 20 needs to be a float number. And next we want to set the left temperature to be 50 degrees Celsius and the right to be 80 degrees Celsius. So we have, and then for our left temperature, we have t index of 1 equals 80 dot. Okay. Now we get to finish our code and see what the Crank-Nicholson method did to our temperature data over time. And for this, we need to start the process of putting together our banded matrix. So we go ahead and state what we want in our matrix box, which is 3 rows to indicate the upper, middle, and lower diagonals. We also want to indicate that the amount of columns that we want is 2 less, since we already have the starting and ending temperatures as set givens. So we have on our new code line, a equals numpy dot zeros 3 comma nx minus 2. Yep. And now that the main structure of the matrix is created, we have to indicate what we're putting in the diagonals that the zeros are going to surround. So in the upper diagonal, we can put in our Crank-Nicholson constant r, but we want to make sure that it's negative so that when we're looking at the equation, the r is flipped to the other side of the equation for t at position j. So we do the same for the lower diagonal. The main quadrant, though, is going to be 2 times the amount of r plus 1, and which is just like what we say in our previous equation. So let's start, and we end up writing a index 0, 1 equals negative r, and this is our upper diagonal. And then after that, we have on a new line, a index 1 equals 1 plus 2 dot times r. There we go. And this is our main diagonal. And after that, we end up having on another line a index 2 comma colon -1 equals negative r. And this is our lower diagonal. And yep, so this next part is imperative to get the vector information and set up and formulated to fit our needs and the math that is going to follow. The first thing that we want to do is set up variable b, which will be used to perform calculations for when we make our figure. To start off with getting the right-hand zeros of ax plus b, which is the linear equation, and this is performed by using NumPy's zeros function. So on a new code line, we've got b equals np dot zeros parentheses nx minus 2. All right, next up, we take the equations from the last part where we found everything for the Crank-Nicolson finite differentiating equation and make them applicable to the matrix in specific non-initial and non-final temperatures in times that we're referencing. So we end up writing in our code b equals r times t index 2 plus 1 minus 2 dot times r times t1 plus r times t. I think it was this, I believe. And so the t index of 2 only calculates using the values of 2 to 5, t index 1 to -1, oops, only calculates values 1 to 4, and t index colon of -2 only calculates using the values from 0 to 3. So next we take the previous value and add our times 10 index 0. So we end up writing underneath that b index 0 equals b 0 plus r times t. There we go. And then right underneath that, I'm just going to copy what we just wrote out and paste it. And we have to replace all the zeros with -1s. So we have b index 1 -1 equals b index -1 plus r times t with an index of -1. All right. So now that all of the adjustments and matrix has been created, we can now create our subplot. So on a new code line, we have fig2 equals make underscore subplots, parentheses, rows equals 1, calls equals 1. All right. And then on another line, we have fig2 dot add underscore scatter with x equals x, y equals capital T, and name equals initial. Can't spell. Initial. Yep. Now we have to create a for loop to run all of our data and make it plottable in figure 2. So we write for I in range nt plus 1. Then we've got underneath that, we indent and have t1 -1 equals solve underscore banded 1, 1. And then we've got capital K, lowercase b. All right. And on another line, and keeping our indentation to line up with that one above it, we have lowercase b equals r times t index 2 and then plus 1 minus 2.0 times r times, and this is times t with an index of 1 to negative 1. And after this is plus r times t index negative 2. There we go. And on another line, still keeping the indentation, we have b index 0 equals b 0 plus r times t index 0. And so then we copy this, and we're going to do the exact same thing we did earlier with replacing all the zeros with negative ones. All right. So we end up getting b index negative 1 equals b index negative 1 plus r times t index of negative 1. All right. And before we print, we need to make sure that we have the perfect amount of points coming out from the matrix, and everything we need has been processed through the correct equations. So this is why we are using a modulo function as denoted by the percentage time. So this determines the remainder when a value on the left of it is divided by the value on the right. So by having I iterations needing to go perfectly in 100, we can ensure that all data is up to date before printing. So starting on the line underneath that, keeping the same indentation, we have if I percent 100 equals 0, we are going to add another line underneath that and indent it. So it lines up kind of with the I, and we've got fig2 dot add underscore scatter, and then we've got x equals x, y equals t, name equals f, with fancy brackets, I times delta t. That's all right. And that's where we run it. And finally, we test for the value of r. So let me just start running this. Oops, 98. Oop, wait, what did I do? NP zeros. Is that what's supposed to happen? Yep, there we go. Okay. Ooh, there's supposed to be another 2 parentheses, possibly. Nope. All right. Module numpy has no attribute zeros. Got zeros. I don't know. Oop. Okay. This was supposed to be an A, and then also I spelled zeros wrong in this. Let's see if this works now. Okay. Let's run it from right here. Shift enter, shift enter, shift enter, shift enter. There we go. Let's keep going. All right, there we go. And then we have R at the very end, and just hit enter, and that's what you get. Thank you very much.